Welcome to week 3, or welcome to the end of week 2, depending on whether you started counting from Wednesdays or Mondays. Any general questions or problems? I do remind you earlier in the week, please do use the survey to choose modalities. Obviously, you can see gaps in the room if you're in the room. So there were some people still who wanted more in-person days. So mostly I need to know who's not coming just so I can reassign people who wanted extra days. So. Any other general issues? Again, technically, the weekly OWL homework is due tomorrow at midnight. So if you have not looked at it, please do. Again, I suggest in general always looking a week ahead. So you should be looking at next week's OWL homework just so you know what's coming and what maybe to pay extra special attention to this week. Any other general issues? Okay, finally, actual atoms and molecules, more or less. You will find, if you haven't noticed already, I'm not a big history of science guy, meaning I don't spend a lot of time talking about who did what and how wonderful they were and what the background was. Almost the only real exception is today, because I think Dalton is an interesting story in scientific thought. And so we were talking last week about the fact that you could separate matter, which is anything that has mass and takes up space, into essentially 3 or 4 categories, depending on how finely you want to divide them. There are these things called atoms, which chemically speaking, we consider the building blocks of matter. There are molecules, which is the matter itself. And if I have more than one molecule, I have mixtures. As we discussed last week, for reasons I don't need to get into again, I am not a big fan of the homogeneous versus heterogeneous mixtures, although there are times when it really matters, right? And so from a chemical standpoint, in everyday parlance, you could say we're just talking about things, right? No souls, no spirits, no ethers, right? Something you could pick up, hold, taste, smell is matter. And ultimately, what we want to be able to do is take some chemical thing and turn it into some other chemical thing, right? And so again, atoms are the building blocks, molecules are collections of atoms, and mixtures essentially are collections of molecules. Now, atoms really do not exist as an entity until the early 1800s due to good old John Dalton, who I mentioned earlier. The word itself goes back to the Greeks, but what the Greeks meant by atoms are not really what we think of today as atoms. And so the first person to really postulate the existence of these things called atoms was Dalton. And it is interesting to me, and therefore I burden you with my interest, right, how he came to this conclusion, because of course, it's not until the last 25 years or so that we could actually visualize single atoms, right? It wasn't really until the 20th century that we could even indirectly visualize individual atoms. Yet in the very early 1800s, Dalton postulated they must exist, and it was based on a few other observations and a little bit of logical reasoning. Right? Lavoisier, who predates Dalton by about 30 years, showed that mass is conserved. These were the innocent halcyon days of old, when chemistry just boiled down to lighting things on fire. But Lavoisier burned a whole bunch of things in sealed containers, and he weighed them before and after the burning, and he discovered no matter what he burned, the total mass always stayed the same. Right? And we know that today as conservation of mass. Right? And so no matter is created or destroyed. And then Proust, who comes a little after Lavoisier, a little before Dalton, made a series of mixtures of different elements, again, a lot of them involving burning. And he discovered that the ratio of the masses of the things he reacted was always the same. So, for example, if you're mixing hydrogen and oxygen to make water, he discovered that if you started with 16 grams of oxygen, it always took 2 grams of hydrogen to completely react with the 16 grams of oxygen, right? And so if you started with 8 grams, it would take 1 gram. If you started with 24 grams, it would take 3 grams. And there was always this 8-to-1 mass ratio between the 2 reactants in his reaction, right? From a modern standpoint, that seems less mysterious because we know about atoms, but at the time, nobody really knew about atoms. Dalton extended this slightly, right? And he noticed that if you made different combinations of hydrogen and oxygen, for example, you could get different ratios. So this law of definite proportions got expanded into the law of multiple proportions. Right? Meaning, for example, if he took hydrogen and oxygen and made water, like Proust, he noticed that there's always an 8-to-1 ratio. On the other hand, if he took hydrogen and oxygen and made hydrogen peroxide instead of water, there was always a 16-to-1 ratio. And so that was 2 different mass ratios for 2 different products using the same reactants. And that, frankly, is all the information Dalton had to go on when he decided that these things must mean, right, that there were these things called atoms, right? The conservation of mass meant that these things were not being destroyed or vaporized or somehow eliminated in the process. And from the definite and multiple proportions, Dalton argues that there must be these individual entities called atoms that join together to form these molecules in what we now know as atomic ratios. And so around 1810 or so, Dalton proposes the atomic theory, which is really still valid with a couple slight tweaks. Right. And Dalton's first and foremost postulate is that each element is composed of atoms and that these atoms must be incredibly small. Right. This was an implication of the definite proportions. If they were big, right, it would make some difference how much water you were trying to make as to whether or not the ratio would hold, right? And the fact that this exact ratio was always holding must mean that they were infinitesimally small. And we still believe this, right? He also postulated, based on this mass ratio, that all the atoms of a given element must have identical masses and the mysterious other properties, and that these masses were different from all other atoms. Again, that is partly an obvious implication of the definite proportions, although different from all other atoms was a bit of a leap in logic. And this is one of his postulates that requires a slight tweak. As we'll talk about hopefully by the end of class today, not every atom of a given type has exactly the same mass. Right. And so if you wanted to modify that statement slightly, right, you would say that all atoms of a given element, right, are identical in the average mass of the elements as opposed to the individual mass, because these are these things called isotopes, which are different atoms of a given element that have different masses. All right. The other one that needs slight modification, although we can still sort of excuse it if we stick to what we consider chemical, is the idea that the atoms were indivisible and could not be created or destroyed in chemical reactions. All right. This, of course, descends from the conservation of mass observation. It is essentially still true in the chemical sense, right? But as you probably know, right, atoms can be divided into subatomic particles in what are known as nuclear reactions. These are high energy physical processes, right? They're not strictly what we consider to be chemical. And so, you know, if I finesse that statement, I can make it still true, right? But as we will talk about very, very shortly, atoms are in fact divisible into smaller pieces. They just don't divide in a normal chemical reaction. Well, stick around till spring and you'll hear me say that in a reaction we barely consider chemical. Nuclear reactions are sometimes included in chemistry, but they're not strictly what you would consider chemical. It's one of those things that's really more physical in chemistry. Because again, what kind of makes chemistry is this idea of breaking bonds. And a nuclear reaction does change your reactants and products, but there's no bond breaking that's going on. All right. I say the same about redox reactions, which is a bigger class of chemical reactions, but those sometimes involve making and breaking bonds, right? But at least in the context of a chemical reaction, my atoms are indivisible, right? And the fourth postulate, which is still true, right, is when atoms of different elements form compounds, the ratio of one type of atom to another is fixed. This is really central to what we do with chemistry because we really don't talk about mass ratios anymore. It does seem, based on my experience with international students, there are some countries that still teach chemistry as mass ratios. Right. And you could. There's nothing inherently wrong with that. But it is far more common now to speak of H2O, which is not a mass ratio for water, it's an atom ratio. If you wanted to construct water with mass ratios, right, it ends up being, you know, HO8, right, in terms of masses, right? And so almost all chemical reactions are now framed in terms of these atomic ratios. And to my mind, that was a huge leap in logic for Dalton to make. And, you know, you cannot find a lot of essentially unmodified scientific theories from the early 1800s that still exist into the present, right? And so one of the things, which I have already said is a challenge in chemistry, is that you do not tend to see atoms. This creates a certain amount of cognitive dissonance if you happen to be learning chemistry for the first time, because you do not have a mental image of the thing we're talking about. right? I sometimes spend a little bit of time talking about basic learning theory, right? But that mental image you have when I say puppy, right, is really intimate with the way you think of puppy, right? Whereas if I say magnesium chloride and your mind's a blank, right, it is very much a much more abstract concept and harder to rationalize the behavior of magnesium chloride than it is a puppy, right? And so one of the things you really want to develop, and it can be in a very basic, unscientific way, is a visual of what the molecules look like. And so there is no molecule that looks exactly like this, obviously. They're not squares and triangles and circles. But it is helpful if when I say magnesium chloride, you mentally see this, which is what magnesium chloride would look like. Not blue colors and gold colors, not triangles and squares, but it is one magnesium atom stuck to two chlorine atoms. Because viewed that way, most chemistry is like playing with Legos. If I'm going to do chemistry with magnesium chloride, I'm going to rip that chloride Lego off and stick something different there. And that's about all I ever do chemically. No matter how big or small the molecule is, I'm ripping a piece off and replacing it with something else. And as silly as it might seem, having that mental image does make chemistry easier. Now, you don't have to buy my mental image. I will draw such things. You can embrace them or not. I had a student last year who told me it was much easier for him to think in terms of actual molecular simulations. I wanted to say, you must be kidding me. Molecular simulations are very, very complicated things. On the other hand, if you've seen enough of them, right, that could be the mental image you have of molecules interacting, right? But having some kind of image helps. And so ultimately, the implication of Dalton's theory is that molecules, the things he was experimenting with, must look something like that. And those Legos are infinitesimally small. All right. Again, it's worth noting, right, his indivisible atoms are really not divisible. If you want to throw a couple more names in there, J.J. Thomson, really about 50 or 60 years after Dalton, right, discovered the electron. And right, what he discovered were these negatively charged particles emitted from his cathode ray tube, right, that were attracted to the positive end of his electrical circuit. And then Rutherford, about 100 years after Dalton, discovered the rest of the pieces when he fired alpha particles, which are actually helium nuclei, protons and neutrons, at a gold foil. And what he found surprised him, which was when he took these essentially massive particles, because helium particles are pretty big, especially relative to an electron, and shot them at gold, right, most of the alpha particles went straight through, right? His comment on this was that it was shocking because it was like firing a cannonball at tissue paper and seeing it go through, but also seeing some bounce back, because he also saw a percentage of the alpha particles that bounced back, right? And from this, we learn that most of matter is empty space, but there are these hard little nuclei, right, that are small, right, which is why the alpha particles go through, but they are hard, which is why some of the alpha particles bounce off them, right? And so we now know, right, that matter, which is made up of atoms, right, is not, the atoms are not all little hard spheres connected, unlike my Lego model, that there are two different regions. Essentially, the hard little nuclei where the protons and neutrons reside, and these layers of electrons, which are actually the soft, sort of empty parts of the atoms, right, often visualized as a cloud, where you can literally poke your finger through the cloud, right, but you cannot poke your finger through the nucleus. And so the nucleus is the hard skeletal part of an atom, but as we will ultimately see, it's the electrons that stick the atoms together, and they represent the bigger empty space part of matter. Right. And so after Thomson, around 1860 or so, 1870, and Rutherford in the very early 1900s, you get to Bohr around 1920, who constructs this model of the atoms as being constructed of three subatomic particles, which again do not tend to come apart in a normal chemical reaction, right? And the protons and neutrons make up the nucleus, and the electrons make up what he modeled as these planetary orbits around the nucleus. This model is wrong. Not to belittle Bohr and his Nobel Prize, right? However, it is a very useful, simple description for what it looks like. And it's not a bad model if you recognize what its limitations are, right? So the nucleus, like the sun, which is of course where he gets this model from, is at the center of the atom. The electrons are in circular orbits like planets. Most of the mass, 99.98% of it, roughly, right? Most of the mass is in the nucleus. That is why that is the hard part of the atom that you bounce off of. And so the protons and neutrons are the massive particles. The electrons are negatively charged, and the protons are positively charged, and they balance each other. And so you essentially have a pair of mass particles and a pair of charge particles. Protons and neutrons make up the mass. Electrons and protons make up the charge. All right. And for the most part, that is not a horrible picture to have. Right? You can sort of see already probably what the flaw in this theory is, right? Because out here I have electrons that are negatively charged. In here I have protons which are positively charged. First and most important rule of chemistry, opposites attract. All right. The electrons should not sit there stably in their orbit. They should crash into the nucleus at some point. And they do not. Right. And so we'll talk shortly, a week or so, I think, if I remember my own schedule, about the slight modification that needs to be made to the Bohr model to keep the electrons from crashing into the nucleus. The other thing which should be true is you've got all those protons in the nucleus which are positively charged. Opposites attract, likes repel. The protons should come flying out of that nucleus, right? I've packed all my positive particles into one little space, right? And so the Bohr model is overly simplistic, but it does get to the nuts and bolts of what's going on. I've got most of the mass concentrated in the nucleus. I've got a charge balance between the external electrons and the internal protons, right? And much of the matter is made up of this light, fluffy, cloud-like electron shell outside the nucleus, which is the part of matter that the alpha particles flew through in the Rutherford experiment. Right. Here's just what I said in words. Right. Ultimately, there are forces missing from it, but I do think, again, for the sake of having a mental image of what the atom looks like, the Bohr model suffices. I don't need a more complicated quantum mechanical model to be able to understand the basics of what's going on, right? And again, the key points are the mass is almost strictly a result of the protons and neutrons because they are far more massive than the electron, right? The charge is a result of the net number of protons and electrons because the protons are positively charged and the electrons are negatively charged. Right. The number of protons, right, determines the identity of the atom. This is very shortly about to be the key concept here for what we're talking about today. Right? Proton number determines identity. Whatever slight difference there might be between two gold atoms, and there are sometimes slight differences, which we'll talk about in a second, they always have the same number of protons. Every carbon atom in the universe has 6 protons. No matter what other differences they have, no matter how dramatic those differences might be, if it has 6 protons, it's carbon, and if it's carbon, it has 6 protons. Right? And so proton number is key to the identification of the species. Right, and as we will eventually talk about, right, it's the electrons that are responsible for the actual chemical reactions. Okay. Questions, problems, are we good? Oh, look at that, we're right on schedule. Yes, no? Okay, now the first of about a dozen things in Gen Chem that I think are horribly named. Right, mass number. Mass number is horribly named because it would seem to be the mass of something. It is not. Right. I cannot emphasize this enough. If anything today causes confusion, it is this. Right? I say mass number, you think mass. The mass number is not the mass of anything. The mass number is simply the total number of neutrons and protons. It is an integer representing the total number of neutrons and protons, period. It is not the mass of anything. Right? Because the protons and neutrons are most of the mass of the atom, the mass number, right, is closely related, right, to what actually is the atomic mass, but it is not the atomic mass. Right? It is simply the integer number of protons and neutrons. Right? And that is important because of the isotope issue. All right. The actual atomic mass is the actual mass of the atoms in some kind of mass units. And so I introduce you today to the second thing that I hate in Gen Chem, which is the quote unquote atomic mass unit. Right. And here's the thing about the atomic mass unit. It is a totally arbitrary unit, which is why by the end of today, unless we slow down a little, in which case we'll use it on Wednesday also, by the end of today, I never want to see, hear, or say the word AMU again. Right? Because here's the thing, I mentioned, right, Dalton postulates the existence of atoms in 1810. Nobody could weigh them until the 20th century, which is why my atomic mass is not in grams here. It's in AMUs, which chemists sometimes joke stands for arbitrary mass unit as opposed to atomic mass unit. Because while they couldn't weigh the actual atoms, what they did know is what the relative mass of them was, right? We talked about definite or multiple proportions, right? H2O is always 8-to-1. Why? Because the mass of oxygen is 16 times the mass of hydrogen, even if I don't know what that is. Right? And so AMU was just a way for 19th century chemists to reference the mass of something they couldn't weigh. And so what they did is set carbon 12 specifically, more on what I mean by that, arbitrarily to a mass of 12. And then they weighed everything relative to that. In the modern era, we have a much better unit for the mass of atoms, which we will hopefully talk about by the end of today. But for now, I will leave it as AMUs because, again, I want to talk about relative masses without having to worry about moles just yet. Right. And it turns out that the mass number is usually close to the atomic mass, but it's always an integer slightly larger than the real mass. So for example, right, if you have a mass number of 24, the atomic mass is usually 23.99 somethings. Right. But again, mass number, not really a mass. Right. Atomic mass, really a mass. Unfortunately, they both have the M word in them. And so I think it's potentially confusing. Right. The atomic number, you know, I don't know why scientists do this, but the atomic number is just another word for the number of protons. Why I couldn't just call it the proton number, I don't know. Right? Maybe an attempt to emphasize that that number is intimately associated with the identity of the atom. I don't know. But atomic number is the number of protons. And again, right, from the Bohr model, right, all atoms of a particular type have the same number of protons. Right? All carbon atoms have 6 protons. Anything with 6 protons has to be carbon. Right? All nitrogens have 7 protons. Anything with 7 protons has to be nitrogen. So in that sense, I really don't even need to call it carbon. I could just say, hey, 6 proton atom. And everyone would know what it was. Right? Okay, and the atomic number is the element number in the periodic table. So part of the goal this week is to get a feel for the periodic table, right? As I said, there's good old carbon at number 6, right? The atomic number of carbon is really telling you carbon has 6 protons, right? If I go down to tungsten, right, its atomic number 74, all tungsten atoms have 74 protons. Right. And so technically I could use either one of those to specify what atom I'm talking about. I can say C for carbon, and we all know what I'm talking about. I could say carbon, C-A-R-B-O-N, if I want to write it out. We all know what I'm talking about. Or I could say it has 6 protons, in which case we all know it has to be carbon. Right. The world would be slightly simpler if all of my atoms also had the same number of neutrons, right? Because then all of my carbons would have the same mass number. Because again, remember, mass number is proton plus neutron. It also means all of my carbons would have the same mass. Right. And again, that was the one thing that Dalton sort of got wrong, right? Because of the existence of these things called isotopes, right? Isotopes are atoms of a particular element that have different masses, right? And the reason they have different masses is because they have a different number of neutrons. Because remember, 99.98% or so of the mass of an atom comes from the protons and neutrons. Right. And so I can say unequivocally, if my atom has 6 carbons or 6 protons, it's carbon. That has to be true. But if I say that, you also can't know what it weighs. Because unfortunately, not all carbons have the same number of neutrons. And so if I want to talk about a very specific carbon atom or type of carbon atom, I really need to specify both because of this isotope issue. All right. And so, for example, there are 3 isotopes of carbon. There's a 6 neutron version, there's a 7 neutron version, and there's an 8 neutron version. All the versions have 6 protons, because again, that's a rule. Right? All carbons have the same number of protons, but as we can see here, they have a different number of neutrons. All right, and this is why this mass number thing exists. Personally, it would be clear if they just quoted it as neutron number, right? In the sense that what's really different here is simply the number of neutrons. But again, for historical reasons, because some of this work predates anybody being able to count the protons and neutrons, right? It was framed in terms of relative mass number, right? And so I've got a carbon that has a mass number of 12. I have a carbon that has a mass number of 13. And I have a carbon which has a mass number of 14. Right? And you've probably heard of at least one of these, which is good old carbon 14, which pops up occasionally in common parlance as a way of dating dead, formerly alive objects. Right, but in fact, all 3 of those isotopes can be referenced by their mass number, total number of protons, total number of neutrons. And so carbon that's 6 and 6 is referred to as carbon 12. Carbon that is 6 protons and 7 neutrons is referred to as carbon 13. And good old carbon with 6 protons always and 8 neutrons is referred to as carbon 14. Or in shorthand, right, the isotopes are written using the atomic symbol from the periodic table and the mass number as a preceding superscript, right? And so if I write C for carbon with a superscript 12 out front, I am specifying only the carbon atoms that have 6 neutrons. Carbon 12. All right. If I want to specify only the carbon atoms that have 8 neutrons, a mass number of 14, I write it as C with a preceding 14. Right? If I just write C, it is all 3 of the isotopes, which frankly is the way most chemistry is done. Right? Because if I scoop up a sample of carbon and don't do anything to it, I expect it to have the normal mixture of all possible isotopes because I didn't really try to separate them. Right? And so most chemistry is just C. Right? On the other hand, I can separate carbon 12 from carbon 13 from carbon 14. There are times I might want to do that. If I do, then I have an isotopically pure sample of carbon, and to write just C would mislead my reader into believing that I have a mixture of isotopes. And so the only time I use C12, C13, C14 is if I have an isotopically pure sample because I separated the carbon isotopes from each other. All right. With me? Oh, I got a thumbs up. Let me take a bow. Right. In somewhat redundant fashion, this is sometimes also written with the atomic number in it. Right, I say it's redundant because, as I've already said probably way too many times, but you can never repeat yourself too many times, right? If it's carbon, it has 6 protons. If it has 6 protons, it's carbon. So if I say C, I am saying 6 protons. There's no reason to write it twice, yet sometimes people do, right? And so in standard isotope form, the preceding superscript is the mass number, protons plus neutrons, and the preceding subscript is the proton number, right? While it's somewhat redundant, it's also somewhat helpful, right? Because if I'm trying to figure out how many neutrons there are, right, this is protons plus neutrons. This is just protons, right? So 12 minus 6 equals 6. Protons plus neutrons minus protons equals neutrons, right? The reason it would be helpful to have both numbers is it gives me an indirect way of calculating the number of neutrons. Right. When I develop a giant death ray and therefore compel the world to do what I want, the first thing I will do is change that to proton number and neutron number, right? I can make it much more direct by, instead of specifying the mass number, if I just put the number of neutrons there, because it would tell you the same thing and you wouldn't have to do any math, right? But as long as mass number is a thing, I do need the proton number to figure out the actual number of neutrons. And so giving you both numbers gives you a pathway to do that. All right. I can also differ in terms of the number of electrons. These are called ions, right? An ion is any atomic species where the number of protons and the number of electrons are not equal. Right? If the number of protons and the number of electrons are equal, they balance and you have 0 net charge. Right? On the other hand, if you've got a couple extra electrons, you have more negatives than positives, you're going to be negatively charged. That is an ion. Right? A negatively charged ion is more specifically called an anion. Right? On the other hand, if I'm missing a couple of electrons, I'm going to have more protons than electrons. I'm going to be positively charged. That is also generically called an ion, but specifically called a cation. Right? Cations are positively charged atoms, right? Anions are negatively charged atoms or molecules, right? And it's really a question of how many electrons you have relative to the number of protons, because of course, if you're carbon, you always have 6 protons, but you don't have to have 6 electrons. Right? And so if I want to completely define all of my subatomic particles for an atomic species, right, what I really want to know, and again, when in Lex Luthor fashion, I get my death ray and compel the lords of science to let me define things, right, I would just tell you the number of protons, the number of neutrons, the number of electrons. Instead, I get a slightly indirect way of specifying the same information, right? I do have the atomic number there, which is the proton number, but then to get the number of neutrons, I have to subtract that from the mass number. And then to get the number of electrons, I have to do a little math also, because the normal way of essentially indirectly specifying the number of electrons is to include the charge on the ion, right? What the +1 means essentially is I have 1 more proton than electrons. All right, it's carbon, it always has 6 protons, right? So again, indirectly, I know if it's a +1, there must only be 5 electrons, right? So essentially, you know, if you want it in terms of math, right, my charge is my protons minus my electrons. And so again, from the proton number and the charge, I can calculate the number of electrons. I've always thought, since I was young and had hair, that it would just make more sense to tell you, you know, 6 protons, 8 neutrons, 4 electrons. But for historical reasons, that's not the way it's specified. And so my most specific symbolic representation for a given type of atom, right, is atomic number, right, mass number, and charge, all grouped around the atomic symbol. Right? If there's no charge there, like the top one, there's implicitly a 0. Right? If I don't specify the charge, it's not an ion. There is an exact balance between the protons and the electrons. But the 0 is not always written. In fact, it's most frequently not written. All right. And again, just to be clear, if I do not include a mass number, like at the bottom, right, then this is a mixture of carbon-12 and carbon-13 and carbon-14. Right? If I do not specify an individual mass number, it is not a single isotope, it is a mixture of all isotopes. And though I wanted to go slightly farther so that I could forever throw away AMU from our lexicon, this is not a bad place to stop, and so we will be stuck with AMUs for another 15 minutes or so on Wednesday. Questions on any of that? If not, happy Monday. Week 3, we're still in session. If you saw Oneonta over the weekend, they only lasted 1 week. There should have been some kind of prize for whichever college could make it through the whole semester without pivoting. We're winning. Happy Monday. If you have individual questions or problems, see me. Otherwise, I will see like 6 of you on Wednesday and some of you from the chat on Wednesday in our strangely split universe.
Yeah, I have a quick question.
Yeah.
So just to confirm, we do have lab today.